Hello, my name is Surania Kunadi, and I'm an assistant professor at the Department of Geography and Regional Research at the University of Vienna and leader of the working group Digital Geography. This video is about spatially conscious machine learning or spatial ML, and I will talk about the applications, the types, and the spatial properties when we do geographical modeling. I will explain what is spatially conscious machine learning. I will give an example of it with a spatial lag model and the application of the model using two spatial datasets. Geographical modeling has been used to predict socioeconomic indicators, land cover classification, climate, atmospheric, and temperature-related information, the spread of diseases, forecasting crime or traffic, and in many more application domains. Spatial statistics or machine learning algorithms are used in geographical modeling and spatial prediction, but they have both pros and cons. Spatial statistics do consider the spatial properties of the data, but they cannot detect nonlinear relationships and there are issues with large-scale computing. On the other hand, with machine learning techniques, these are scalable, can model nonlinear relationships, and overall give good accuracy and predictive performance results. However, they do not consider the spatial properties of the data. Now we'll explain why this can be an issue when predicting spatial data. I will use the Simpson's paradox that requires three variables: the dependent, which is the information that we want to predict, the observed or independent variable, which is the information that we use to make predictions of the dependent variable, and the lurking variable, which is a missing or a hidden variable. The statement is that the relationship between the dependent and observed variables cannot be detected, or it is inaccurately detected because of the missing lurking variable. As an example, our dependent variable is the prices of houses at different locations, and the observed variable is the population density at those locations. The assumption here is that the higher the population density, the lower the house prices at those locations. However, we cannot detect the pattern when we analyze our data. The reason being the lurking variable, which is, in this case, space. When we divide our samples in two areas, for example, area A and area B, we can detect the previously assumed negative linear relationship. But this relationship is also different in the two study areas. So space is very often a lurking variable in geodata, and that is because many spatial processes differ from random. They exhibit properties that we call spatial heterogeneity and spatial autocorrelation. This map in California state shows the samples locations that were used in a regression task. The 5 colors that we see here represent the spatial groupings of the residuals of the regression. I will not explain all the groupings, but let us focus, for example, on the red points, the high. These are residuals that are high in value and they are surrounded by other high residuals. We can see on the map that these are concentrated around the coast area and they are not randomly distributed in space. This shows why non-spatial models like machine learning models may lead to biased or not optimal results. So spatially conscious machine learning or spatial ML in short aims at merging spatial statistical methods with machine learning algorithms to take the benefits from both. The research on spatial ML focuses on 3 directions. First one, the engineering and inclusion of spatial features in machine learning algorithms. Second, the creation of hybrid models. That means merging machine learning algorithms with geostatistics, spatial statistics, or for example, regionalization methods. Third, spatial cross-validation strategies for interpolation or extrapolation of geodata. One spatial machine learning method is the Spatial Lag ML. This method involves the engineering of a spatial feature, the spatial lag, and incorporating it into a machine learning model. It is a straightforward approach that does not require the modification of the algorithm and can be extended to other models as well. Okay, so what is exactly the spatial lag? Spatially lagged variable is a weighted sum, as we see here at the top, or a weighted average here of the neighboring values of that variable. It is like a smoother of a variable in the area, and it is being used in statistics to capture or measure the spatial dependence in the data. In the example here, at the top are the variable values and at the bottom the spatial lag values. So this spatial unit here has a spatial lag of 5 if an equal weighting scheme is applied to all the neighbors, and neighbors are the spatial units that share an edge or a vertex to that unit. Keep in mind that there can be different ways to calculate the neighbors and the weights. The spatial lag feature was inserted into a random forest model and applied in two different datasets. On the left is the MeUse river dataset used to predict zinc concentrations around the river. On the right is the California housing dataset that is used to predict house prices at these locations. These two datasets were selected because they represent a small and medium-sized spatial datasets and because they have been used previously in other spatial prediction studies. We see the results of the models and we compare their root mean square error. As nested cross-validation was used here, in this case with 5 folds, the test error of each fold and the average test error was calculated. The error is compared across 3 models. The non-spatial machine learning model, which is the pure random forest model, the spatial lag model, which is a random forest model that includes the spatial lag variable, and a benchmark spatial statistical model. In this case, geographically weighted regression was used, or in short, GWR. These 3 models are compared for both the MeUse as well as the California datasets. If we look at the average test error, we can see that the GWR model in the case of MeUse performed a little bit better than the spatial lag model, whereas for the California data, the spatial lag model performed a little bit better than the GWR model. And in both cases, the spatial lag model and the GWR model performed better than the non-spatial, the pure random forest model. Keep in mind that this area of research does not look at causes and effects. The focus is on improving predicted performance. Also, depending on the situation, spatial statistical methods can still be a simpler and better choice. Future improvements may involve testing more algorithms, creating modeling workflows that are applicable to both discrete spaces and continuous surfaces, testing methods in more domains, combining and further tuning previous spatial machine learning efforts, investigating more spatial forecasting tasks, and also evaluating what works better for interpolation or extrapolation spatial predictive tasks. Thank you for watching the video on the spatially conscious machine learning, Spatial ML. If you want to know more about it or the work that we do in the digital geography group, please read the description below.